Now we want to look at the second derivative and what it means for us when we want to look at graphs of functions. And we remind ourselves first that the first derivative of our graph gives us the gradient of our curve. So the first derivative is the gradient. Then the second derivative there, it will always describe the concavity of the curve at the point. So the first derivative will always describe its gradient. It gives us a gradient function. The second derivative gives us a concavity function. So it will describe the concavity of a curve at any point. So, for example, and we know how to get the second derivative. We just take the derivative of the first derivative. So we have our function, we derive it, then we derive it again. So x cubed derives to 3x squared, derive 3x squared becomes 6x. 3x squared derives to 6x, which then derives to 6. The minus 4x derives to minus 4, and minus 4 derives to 0, and 5 already derived to 0. So we've got our gradient function and our concavity function. And that's what the derivative is going to tell us every time. So there's just some practice on getting the first derivative and then getting the derivative again. So get the derivative of each term and then the derivative again. So if you've got to use the product rule or the quotient rule twice, it's a bit ugly to do it, but unfortunately we might have to do it. So the chain rule, product rule, quotient rule can be used twice to get our second derivative. So what does it mean when we see different values of our second derivative? So the second derivative, we said, describes concavity, and if the second derivative is less than 0, the curve will be concave down. So any part of the curve that's concave down will have a negative second derivative. And if it's, let's go to the other side, if it's positive, it's going to be concave up. Where it's equal to 0, that's where we will have a point of inflection. Now, we say that with a little trepidation, because not always will you get a situation where you've got the second derivative equal to 0 and have a point of inflection. Now, most of the time you will, but not always. So we'll give you an example in a moment of that, but just be wary that that's where it changes concavity. We will have a second derivative equal to 0, but not always will a second derivative equal to 0 indicate a change in concavity. So just be wary of that. So using calculus here, we know that curve is a parabola, and it's concave up parabola. So you can show this using calculus. So you get the first derivative, derive it again, and the gradient's always positive. The second derivative is always positive. So that means the second derivative is greater than 0 for all values of x, so it must be concave up at those points. So what would it look like? Well, that's what our curve starts to look like there. So if we've got a second derivative equal to 0, then that's where it's going to change concavity. But what we need to do is we need to always test either side to make sure it does change concavity. And for an example of one that, if we take this curve here and you're looking at that, well, that's a parabola. Well, no, it's y is equal to x to the power of 4. And this is one of the small number of cases where if we get our first derivative, it will give us 4x cubed. So we know it's stationary there, because when we set our first derivative equal to 0, x would equal 0. We can see that it's stationary. But also if we take our second derivative there, then that gives us 12x squared. Now, when we look at that, that's always concave up. But if we set the second derivative equal to 0, that gives us x is equal to 0, which gives us a bit of a false positive as such in this case. So not always will it be a case where you get the second derivative equal to 0 and get a change in concavity. That's why we need to check our concavity either side. So if I tested my concavity with a negative value of x and then a positive value of x, I would get no changing in sign of the concavity. For it to change concavity, it needs to change from being concave down to concave up, or vice versa. So there needs to be a different sign on either side of the concavity there. So that would tell us as well, and similar to what we did with the first derivative. So that's what we need to do to tell us if there's an actual point of inflection every time. So just be wary of that. So the second derivative is talking about concavity, and if it's concave down, it's a negative second derivative, concave up, positive second derivative, and if it's 0, possibly it's a change in the concavity and a change in inflection, point of inflection.